Thank you a lot for the invitation. Give me the opportunity to explain this kind of quantum gravity without any Planck constant. Okay? So, I have a little problem of auditions. If you ask questions, certainly I will not understand them. Okay, so. This is a work with Professor Eva Cukry from Poland. And also I am not only in Paris City, but in Białystok in Poland. And I would like to start with this quote from Einstein and Rosen from 1935. Every field, in our opinion, must therefore adhere to the fundamental principle that singularities of the field are to be excluded. Yeah, because the singularity we cannot measure. Okay? We just idealize for the model. So this presentation comes from a series of work, especially from this one here with Gilles Cohen-Tanucci, Celestin Bonimana, and Professor Shabani from Bujumbura, from Burundi, and Gilles Cohen-Tanucci from Paris. Only 3 sections. So first I will just give an idea about what I call Gabor quantization. The material is repeated many times here. So just I will make a summary. And I will apply that to the 8-dimensional case, which is involved in general relativity. And I will give an example with 2 + 1 Minkowski spacetime. So, Gabor POVM quantization, just a material. So, on this material, you know very well in this meeting, because we start from some signal in square integrable functions on the line, and we transport, we shift, and we modulate. Okay? So in my notation, U B omega is actually what is denoted by many persons here, pi of z. Okay? So now we pick just a unit trace bounded operator, Q0, for instance, one-rank operators, with psi which is well localized. So if we transport this operator by using precisely the modulation and shifted operators, we solve the identity in this way. Okay? And we can use this resolution of the identity, which is called the POVM, normalized POVM, to quantize functions or distributions defined on the time frequency plane. Okay? And we get an operator, so depending on the function we have chosen. Okay? So we get a quantum realization of the time frequency plane. And we go back to the time frequency plane, I mean in terms of functions on it, by this, the next slide, I'm sorry. So before, there is an alternative formulation of this kind of representations of the operator. It's this one, which involves the symplectic Fourier transform of the function, the original function f. And here you have what we call the Weil transform of the original operator I have chosen. Next, we go back to the time frequency representation of signals, starting from an original one, and we go to another one, which is a kind of regularization by taking the trace of the quantization of f times the translated, modulated version of Q0. Okay? And you have here a realization of this new function, which is in general more regular, and which can be expressed as a tensor, the convolution product here of two symplectic transforms of the function pi. And here you have a nice probabilistic interpretation on the quantum side of what? Of the fact when we consider the plane, the most basic symmetry is the translation. What is the translation? You can choose the origin where you want. That's all. Weil-Heisenberg is precisely the quantum version of this symmetry. That's all. Okay, okay, so let's go to the 8-dimensional case, like we have in general relativity, but also with electromagnetism as well, wave equation and so on. So the phase space is made of space-time variable and the dual, that means wave vector and frequency. And we can put that in some exponential. You don't need any Planck constant here. That's all. Omega is the inverse of a time. Okay? And in this context, of course, we have a perfect time operator, because the frequency goes from minus infinity to plus infinity. Okay, so again, I repeat the quantization I explained in the 2-dimensional case. Sorry. So I consider functions on space-time and wave vector frequencies. So we are the R to the 8. We choose, for instance, rank 1 operators. We transport it and modulate it, and we get a quantum version of this function. Okay? And the way this operator acts on signal defined on space-time, it is an integral operator where the kernel is defined in terms of partial Fourier transform and the quadratic expression in terms of the original psi you have chosen. Okay? And we go back to functions defined on the space-time times the wave vector and the frequency by using the procedure I explained before, but it's just a kind of averaging, local averaging of the original one with respect to this probability distribution in the phase space. So, if we consider just the functions which are defined on the space-time, the corresponding operator through Gabor quantization is just a multiplication operator, which is a convolution. The multiplicator is given by a convolution of the original U with the modulus squared of the probe. I call that a probe, okay? So, like a glass, you know. And if I go back to the semi-classical portrait, okay, here, so I get double convolutions where you still have U, and here you have actually the autocorrelation of the original modulus squared of time. Okay? So, now, if we consider the space-time variables under this process, trivially we get multiplication operators by the component of the space-time event here. Okay. On the level of semi-classical portrait, we have just a shift of the original component by by an average value of x mu with respect to the autocorrelation of modulus squared of psi. Okay? So for instance, if we use, as expected, psi as a Gaussian with 4 variables, and here you have for each factor some width. Okay? So here we get this formula, which can be very easily implemented. And of course, when we apply that to the space-time metric, which is for in general relativity, defined in this way, the metric element is given by g mu x, dx mu, dx mu. G mu is a field, is a gravitational field. So let's apply this procedure of quantization to this field. Okay? So what we get, we quantize, we get a multiplication operator. In general, this multiplication operator will be a regularized version of the original one. And in order to consider that as a function, we go back to the semi-classical portrait. Okay? All depends, of course, on the choice of the probe. The probe, they are my glasses. It is my microscope, you know. It's my way to analyze my environment. Okay, so if we are in Minkowski space-time completely empty, G mu is just the ordinary metric -1, 1, 1, 1. You know, it's the same as driving on the left, on the right. You have in the physics community people who consider this convention of sign. Other people, you multiply everything by -1. So we like confusions in physics and in mathematics. So what we get, we quantize, we get just the set of 4 identity operators. Now, if we go back to the semi-classical portrait, we go back to the original G mu. Nothing changed. Now, if you decide to use, instead of Cartesian coordinates, if you decide to use cylindrical for symmetry reasons, okay, in that case, we will get something. We will get smoothing of the singularity of your system of coordinates in this way. Okay. You start from the original metric, -1, 1, rho squared 1, cylindric coordinates. We choose Gaussian with this set of width. And when we calculate the operators, we get -1, 1, but here, instead of rho squared, we get rho squared plus sigma squared. So we have solved the singularity. The same for spherical coordinates. Spherical coordinates we use all the time when we decide to analyze the influence of a body at a certain point. Okay? The same, you have this kind of regularization for the operators here and for the phase space portrait of the metric. You can see the fact you add to r squared 3 sigma squared, the fact you add to rho squared 2 sigma 2, you are going to change radically the geometry of your space-time. So let's go to the Einstein equation, where the Ricci curvature tensor is built from precisely the G mu nu, the metric field, and here too for R, okay, which is a scalar curvature. So on this side you have the geometry, and on the other side you have the matter, energy, okay, the source, and all that. So you start from this equation, so you have extremely famous equation, of course, and with millions, billions of papers where people try to use specific metrics to interpret what we observe and so on, and in particular black holes and so on, okay? But most of the time, we introduce the devil, that means the singularity, like the original one, which is the Big Bang. It is just a singularity. Okay? It's a singularity in your head, not in reality, I think. Okay, so we make this kind of game. We quantize the G mu nu, we choose a probe, we choose, for instance, Gaussian with sigma, okay? And we quantize, and so now, the new, by going back to the classical phase space portrait of the quantized G mu nu, we have a new Ricci tensor, and so on. But if we have a new one, the semi-classical portrait, we have a new. We create something new, virtual, due to our instrument of observation. Okay? In general, as I show you with cylindric coordinates or spherical coordinates, which are completely trivial choice of coordinates, usually we regularize this kind of singularity, artificial singularity, which is provided by the choice of a specific system of curvy linear coordinates. Okay? So the philosophy we can extract from this game is the following. Specifically the second item, the notion of emptiness for space becomes relative. We are in relativity. Since any quantization of the above Gabor type introduces matter, virtual matter. However minute it may be, this matter arises from the lack of information which is encoded in the parameters of the probe psi. Because when I decided to put one origin of the space here, in order to put a mass, it's never exact. Just again, a kind of mathematical idealization of our environment. Okay? So the probabilistic nature of these parameters should reflect our inability to reach exactness of information about the observed system through data and interpretative model. So again, you have a kind of principle of relativity which is not the original one. Okay? So let me now just finish this talk with yes, we have some time with a specific example here. To simplify, we took 2+1 Minkowski spacetime, and we are going to play with precisely polar coordinates for the space part. Okay? So, I think I should put, because this is a new metric, this is the original metric in polar coordinates. Here you have the time, but now I should put a white check here. The new metric, the same for the two first terms, but for the last term concerning the angle, we had sigma squared. Sigma is the width of the Gaussian. Okay? So the new Ricci tensor is the following one. The Ricci scalar is the following one. You can see this negative curvature decreases as R increases, but remains significant near R is equal to 0, showing the localized impact of the parameter sigma. So now, what will be, from the Einstein equation, the new T mu nu? Is precisely this one. So you have created precisely the time component which corresponds to negative energy. Okay? Just due to sigma. So this is just trivially the way this component behaves with R, with the radial coordinates. Okay. Now, precisely, we have a new metric, just because we use the polar coordinates. What will be, with the new metrics, the geodesics? Okay. If sigma is equal to 0, of course, the geodesics are straight line. But if you put sigma different of 0, the solving of the equation of geodesics is not immediate, but anyway, we can do that. It's a matter of calculation of the first or second year of the university in the old time. And so we end with those equations for R prime and theta prime. We choose S as a fine parameter along the geodesics. And we have the appearance of two constants from conservation law, capital F and capital G. Capital F is connected with the conservation of the angular momentum. Capital G is connected with a kind of energy. Okay? So the final solution, this is a solution of R in terms of theta, and this solution involves precisely Jacobi elliptic function. And when sigma is equal to 0, we go back to the straight line. Okay? So, when F is equal to 0, no angular momentum, regardless sigma and G, we still get straight line for the geodesics because the angular momentum is 0. But if F is different of 0, there is a forbidden region given by this, this inequality. F squared over G squared should be larger or equal to sigma squared. Okay? So when sigma is equal to 0, we have a boundary F over G. Okay, you can see. And for non-zero angular momentum, okay, you can see you have a curved geodesics, more and more. And when sigma increase, when sigma is yes, when sigma increase, so the radius of the forbidden region diminishes until here the particle following some geodesics can reach the center. Okay? And as the sigma increases further, beyond the point where you have sigma is equal to F over G, when you have this kind of, I don't know if I can say the black hole, the forbidden region, okay, the geodesics begin to straighten out again, and they are going to resemble again to straight line. So behind, you know, independently of this context, the fact when you choose polar coordinates, you introduce a singularity at 0. Okay? As you know, theta is not defined at 0. So if you regularize, you change completely the geometry. This is very important to understand. That appears very inoffensive to choose polar coordinates, but it's not. So here you have, again, other examples. Okay, when sigma is small, and so on and so on. When we consider large kinetic energy, and so you can see the geodesics become extremely curved. Okay. Okay, so that's the end of my talk. So with some comments. So the introduction of probe, sigma is the width of Gaussian, but I can choose any kind of probe. It's not confined to a Gaussian. Okay, as an analogous effect to the presence of a central mass within the system, a kind of virtual mass. But again, what is the real mass? What is the virtual mass? You have the relativity principle, which is used to or lack of information. So this sigma functions as a source of gravitational attraction, thereby modifying the curvature of spacetime. This modification results in deformed geodesics and the emergence of a prohibited region. Depending, of course, on sigma. So maybe we can, I think I made a mistake. It should be c squared over g here. I don't know why, but I'm sure you noticed the mistake. Okay, so thank you for your attention. And here, it's not my team. It's not my team. I'm sure you don't recognize all of them. This one, yes. Ah. But I think this one, that could be. This one. No? The bag. The next one, I'm sure you know, but he does not do that. This one, Rosen. This one, yes. No, why? This one is Heisenberg. This one is von Neumann, Wigner, and this one is Gabor. The first one, of course, Fourier, Gauss. Ah, this one, Lee. Yes, because I introduced the Weil-Heisenberg group, which is the Lee group. All those people, they are in my talk. Ah, this one, this I don't remember. Before Boltzmann. Oh, Christoffel. Okay, thank you.